Before we start with the topic of this session, I want to give a clarification for the last session in the morning. So in my last slide, I described the extending oblivious transfer result of Ishai, Kilian, Nissim, and Petrank. And I said that it's not fully simulatable, but the truth is that it is fully simulatable. There are, however, two issues with that construction. One is that the security is based on a rather non-standard security assumption, which they call correlation robustness. However, it seems that most modern hash functions should have that property. That is, it seems that most modern hash functions will have this property that they require. And another issue is that the security against malicious adversaries in that construction is based on a cut-and-choose protocol or paradigm, which I won't describe, but basically if you want to have security of 2 to the minus s, namely to limit the cheating probability of the adversary to 2 to the minus s, you have to repeat the protocol about s times. Okay? So this might be reasonable in some applications and maybe less reasonable in other applications. But apart from that, it's a very nice way of achieving computing any number of oblivious transfers by doing just k of them, where k is a security parameter. So here we're going to talk in this session about protocols for specific functions. So far in this winter school, we talked about generic constructions. But basically we said take any functions that you want to compute, represent it as a circuit, either a binary circuit or an arithmetic circuit. And then the circuit is composed of gates of this and that type, and we'll show you how to compute these gates, and then you can compute the circuit, and therefore you can compute any function that you might want. So this is very good for feasibility results. And actually it's also good for many actual functions that you want to compute, but it's not always sufficient. So let's look at Yau's protocol, which computes a Boolean circuit. And suppose we want to compute, to solve the millionaires problem, where there are 2 millionaires and they want to find out which one of them is richer. So basically what they have to do is compare two numbers, okay? And say if these millionaires have up to $100 billion to each one of them, so to present these numbers you need something like 37 bits. So they should compare two 37-bit numbers. How big should the circuit be? So it's not very large. The comparison can be linear in the length of the number, something like 37 gates. So that's very, very nice. Okay. So also you need an oblivious transfer for every input bit. So you also need 37 oblivious transfers. That's not bad at all. What about other functions? Suppose you have two parties with very large input sets. Say each one of them has 1 million items. So let's think of different functions. Say we want to compute the maximum value of these two input sets. So what can we do? So we want to compute the maximum of all items in the union of Alice's input and Bob's input. Each one of them has 1 million inputs. So what can we do then? So, yeah?
Compute the max of each set and then compare them.
Yeah, so what they can do, Alice can compute the max of her set, Bob computes the max of his set, and then they should just compare two numbers. So that's very nice. Suppose they want to compute the average. So if the sets are of equal size, they can compute the averages of their sets and compute the average of these two numbers. And it's easy to show this doesn't reveal more information than... actually, you can compute the average of these two numbers without any secure protocol. It doesn't reveal more information that you already know, but I won't go into that. If the sets are different sizes, you might want to give a weight to every average, but that's not very expensive. What about computing the median of the numbers in both sets? So here it might get a bit more complicated, because Alice might compute the median of the numbers in her set. But then it might be that all the numbers that Bob have are much larger than Alice's numbers. So the median is in a number which Bob has. So actually, we don't see any clear relation between the medians of these two sets and the median of the union of the two sets. Okay. Also, what about the intersection of the two sets? How we can do that? We might try to use a circuit, but the circuit might be too large. So in this talk, I'm going to discuss two specific functions and describe efficient protocols for these functions, which might use generic circuit-based constructions, but just as limited building blocks. Most of the work is done by observing the function and checking what to do with them. And I specifically look at the median and the intersection. So in general, we have generic secure computation using circuits. As I said, it's efficient if the circuit is not too large. What does it mean a circuit is not too large? So for instance, there are results on computing the AES. So results with Thomas Schneider and Nigel Smart and Steve Williams. We designed the circuit for AES, which takes about 33,000 gates. And computing it on a system, well, with security against semi-honest adversaries takes about 7 seconds. Against covert adversaries, which we haven't covered, it's something like 60 seconds, and against malicious adversaries, something like 1,000 seconds. Okay? This was like 2 years ago, now it's faster. There's a different result of Ivan Damgard and Marcel Keller, who they do computation of AES using arithmetic circuits in a setting with 3 parties, not 2 parties, and it takes them about 2 seconds. Okay? So this is quite impressive because AES is a rather complex function, and yet we can compute it quite efficiently. But it seems like, okay, for 33,000 gates, we need something like 7 seconds. So if we have a circuit with 1 million gates, it might be quite more time than that. Although part of the time is consumed by the oblivious transfers, and there the overhead just depends on the number of inputs, not on the size of the circuit. But it's obvious that if the circuit becomes very large, we need other solutions. Think about a party which has 1 million inputs, each one of them is 20 bits long. Wants to do something with each one of them, we have 20 million bits as an input. Are we in trouble if we're trying to use circuits, just circuits and nothing else? So let's look at these 2 examples. The first would be computing the median security. Okay. So the median is just one example of computing the kth element of a set. So the problem is the following. We have Alice and Bob with private inputs SA and SB, and they want to compute the kth element of the union of these 2 sets, kth being a number. So the 10th element is the 10th largest number in the union of these 2 sets. Okay? So a priori, none of them knows whether the 10th number is in Alice's set or in Bob's set, and they want to compute that number. Why is that interesting? So it might be interesting if they want to do some statistical analysis of the sets. Say you want to compute some histogram, like the 10th percentile has salary this and that, the 20th percentile has salary this and that, and so on. So they have large data sets, and they want to compute some statistical analysis of it. So okay, it's obvious that if we compute the kth element, we do reveal some information. Okay, so look at this example. Suppose Alice has 1,000 values sorted, and suppose she learns that the median of the union of her set and Bob's is the 400th element in her set. So then she thinks, okay, I have 400 elements smaller than this number, and 600 elements larger than it. The median is the value which is exactly in the middle, right? So therefore, Bob must have at least 200 numbers smaller than this median, okay? Otherwise, it won't be the median. It might be that Bob has 300 numbers smaller than the median and 100 numbers larger than it, but it must have at least 200 numbers smaller than the median. So some information is leaked, okay? But suppose we're willing to compute the median and reveal some information, we just want to do it efficiently and not reveal anything more than what the median reveals to us. So we can try doing it using a circuit, but the circuit might be very, very large. Okay? And just computing the kth item, if we have 2 sets of size n, we want to compute the median, that's the nth item. So the circuit should be at least of size n, which might be very large here. So before looking at the secure protocol for computing the median, let's look at the insecure protocol for that task. And something which is very useful to remember is not that the median is the number whose index is just, if we sort the numbers, it's in the middle. The property which is very useful to think about is that the median is the number which has the same number of items larger than it as the number of items smaller than it. So if x is the median, then the number of items above it and below it is equal. Okay? That's the important thing. And we'll first show how to compute the median, then we'll think about computing the kth element where k is different than the median. So suppose they have these two input sets of Alice and Bob. Suppose that all items are different, and Alice sorts her input, and suppose that the median of her input is MA, and the median of Bob's input is MB. And okay, now they should do something. So what they do in an insecure way is compare these two numbers. That's not a good color for the font. And suppose they learn that Alice's median is smaller than Bob's median. Then I claim that immediately Alice can get rid of all items which are smaller than her median, and Bob can get rid of all items larger than his median. Why is that? So recall that the median is the value which has the same number of items larger than it as the number of items smaller than it. If the median was in this set, okay, then it already has half of Alice's items larger than it, and also at least half of Bob's items larger than it. So it has actually more than half of Alice's items larger than it, and half of Bob's items larger than it. So therefore, the number of items larger than any value here is more than half the total number of items. The same is true here. For any item here, the number of items smaller than it are more than half of Bob's items, and at least half of Alice's items. So it's more than the half of the union, so therefore this value cannot be the median. So we can get rid of these two. And one note, okay, there's of course here the boundary problem. I'm talking about smaller, but what happens if the number of items is smaller and equal then? So suppose I have a total of 100 items. Is the median the 50th item or the 51st item? Okay? So just let's define whatever we want and forget about it because it's easy to handle these boundary issues. Okay, so suppose there's exactly the same number of items larger than it as the number of items smaller than it. So the parties can decide after this comparison that the median is definitely not here and here. So they can just throw these items and continue the protocol just with the items which are remaining, these items and these items. Okay? So basically we did here reduction from computing the median on a set of a certain size to computing the median of a set of half the size. And now, of course, we can repeat this process, do it over and over again, make the set smaller and smaller until we find the median. So this is an insecure protocol for computing the median, okay? And it takes log n rounds for sets of size n. But it works. This is another way of showing this protocol. So each party finds its median. They compare the medians. If Alice's median is smaller than 3, she throws all items smaller than her median, and Bob throws the items larger than his median. Otherwise, they do the opposite, and they do it again. So that's the protocol. This is the insecure protocol. And I claim that in order to make this protocol secure, the only thing we need to do is to replace this comparison with a secure comparison. Basically, run here a comparison which does not reveal MA to B and MB to A, but just rather only reveals to the parties a bit saying which one is larger, Alice's median or Bob's median. Okay? So first, in order to compute the function, indeed, all that they need to do is get that bit. So even if we replace this comparison with a secure comparison, they can still compute the median and do the protocol. The question is whether the fact that we reveal this bit to the parties reveals to them more information than just the output that they should get, which is the final median of the union of the two sets. So let's see what happens. So I'll give you an example. So this is the original sets of size 16. Suppose they compare these values. Suppose they learn that Alice's median is larger than Bob's. So she throws all items larger than her median, Bob throws the items smaller than her median, than his median. They continue, now it's the opposite way. They throw items until they get to the final value, which is the median. Now I want to claim that this is a secure protocol. Now in the ideal model where we have a trusted party, okay, all that the parties learn is their inputs and the final output. So in the ideal model, all that they learn is this input and the final output here. So let's go. This is what happens in the ideal model. So in the ideal model, Alice knows that this is her input, and she also knows what's the median. Okay, so it's someplace around here. It's this value. That's all that she knows. In the real execution, if I go back one slide, she also knows what happens in these comparisons in between. But we'll show here that this doesn't reveal that just from the final output, she can actually learn by herself or simulate what would be the answer of the comparisons in between. And why is that the case? So she looks here, says, okay, I know that the final median is smaller than the median I have here. Okay? So in the first comparison, it must be that my median was larger than Bob, because then I would throw this half. If it was the opposite way, I would have thrown this half, which contains the final median that we compute. But then I wouldn't get this answer, which I get as the final answer. Therefore, in the first comparison, it must be that, okay, that's the median. In the first comparison, it must be that I throw these values. Now, what happens in the second comparison? Here it must be that my median is smaller than Bob's, because otherwise I would have thrown the half which contains the final median. So therefore, that's the result, and so on. And she can go on and compute all the intermediate results just from the final result. So basically what I showed you here is a security proof. But this protocol, at least in the semi-honest setting, is secure. It doesn't reveal anything more than you get in the ideal setting. So actually what I did hide here is that we do run secure protocols here using the circuit for doing all these comparisons. But you use them in a black box manner. Okay? The main idea here is this observation about the median and the intermediate values. So this is a protocol for the semi-honest setting. For the malicious setting, which we'll cover in a minute, it's a bit more complex, because you must make sure that the parties give you good answers. For instance, legitimate answers. Suppose that here Alice reports a median of 100, say, and she is told to throw away all items which are larger than 100. Then in the malicious case, in the semi-honest case, in the next phase, she must report a median which is smaller than 100, because she should have thrown away all items larger than 100. In the malicious case, she can report anything that she wants. She can report a median of 1,000 in the next step, which will make this protocol inconsistent. It won't output the right value. So we'll have to handle this for the malicious case. But this will be in a minute. Before that, let me just generalize this protocol. So I described to you how to find the median, right? Sometimes we don't want to find the median, we want to find the kth item, say the 100th item. So how do we do that? Suppose that we have two input sets, and we want to find the k items. So first of all, if one of the sets is larger than k, it has more than k items, we can sort it and throw all values after the first k values. Because it's obvious that the kth value of the union it won't be in any value that has already k values smaller than it. Okay. Now, this smaller set here is smaller, this set here is smaller than this one. And actually the previous protocol I described works only if the two sets are of identical size. So we should make this set larger, but we must do this without changing the value of the median of the union of the two sets. So what we can do, we'll add, or without changing the value of the kth item. So what we'll do, we'll make this set larger as this one, okay? And do this by adding numbers with the value infinity. Say the largest numbers we have in the range. Therefore, the kth value won't be one of these, it will be one of the original values, therefore one of the items in the original inputs that we have. So now we have two sets of size k. We want to find the kth item, which is essentially the median of these two sets. So we're almost done. One other issue we have is that the previous protocol I had was for computing the median of two sets whose size was a power of 2, because we had to halve the sets each step. Okay? And here k is not necessarily a power of 2, so we can enlarge the sets to be of size which is a power of 2, and we can do that by adding, say, to the first set the right number of values equal to minus infinity, and to the second set values of which are equal infinity. So we added the same number of small items and large items, and since the original median was the one which has the same number of items larger than it and smaller than it in these sets, okay? Now we add the same number of items larger than it and smaller than it, so therefore the median remains the same. We didn't change the median. So now we have two sets whose size is a power of 2. We already have a protocol for finding their median, and their median is the kth element of the original inputs we had. Okay. Another issue is, suppose we want to find the kth item, and we don't want to reveal the size of the input sets. We want to find the 100th item, but I don't want to tell you how large is my set. So, okay, if we look for the median, we have to look for a median of a set whose size is 2 times k. The kth item will be that median. But I don't want to reveal k to you. So what I do, let S be some power of 2, which is an upper bound of the size of the two sets, and I just blow the sets to be of larger size by adding the exact number of plus infinity and minus infinity values. So therefore the median of the original sets is the same as the median of these larger sets. So now we can look for the median of these sets. So basically, I guess here it's for defining the median of these two sets, original sets, not the kth value. But I can reduce the kth value to the median as I described to you before. Okay. It leaks an upper bound on the size of the sets, but suppose that's something we're willing to leak. And I guess you can. I guess if you're using a computer, there is essentially an upper bound on the number of items you can use, depending on the computer you're using. Okay. So now we want to do a protocol secure against malicious adversaries, which computes the median. And as I told you, a major issue that might happen here is that the parties might provide inconsistent answers. Say, Alice is told to remove all items whose value is greater than 100, and then the next step she reports a value of 1,000 as her median, or vice versa. If she has to remove all items smaller than 100, she reports a median of size 10. Okay? So we don't want this to happen. So basically, we have to check at every step that Alice and Bob provide consistent inputs with what they had in the previous rounds of the protocol. So here's the modified protocol. So we'll initialize bounds, lower bounds LA and LB for Alice and Bob, and upper bounds UA and UB for both of them. And initially, the bounds will be minus infinity and infinity. So these are bounds on the legitimate sides of legitimate values in the sets. Okay? Now, in every comparison, we will not only check that whether MA is smaller than MB or vice versa, we'll also check that MA is between the bound LA and the upper bound UA, and that MB is between LA and UB. Okay? So this is, of course, in the first step it's going to happen. It's going to be true, but after we make a comparison, and suppose we find out that MA is greater than MB, and therefore Alice is told to throw away all items greater than MA. Okay? Then what should the protocol do? The protocol should set the upper bound on Alice's inputs to be MA, because we told her to throw away all items larger than MA. in addition, the protocol should put a lower bound on Bob's inputs as LB, because in that step we also told Bob to throw away all items smaller than MB. Okay? So in each comparison, as we tell the parties to throw away items, we set bounds on the values of items which they are allowed to keep in their inputs. And then the next step, we make sure that if Alice reported a median of size 100, and we told her to throw away all items greater than 100, then in the next step, in the comparison, we check that the value that she reports is smaller than 100. Okay. So how do we implement this? So we shouldn't reveal these bounds to the other parties. We shouldn't reveal a bound on Alice's input to Bob, because then he learns what the exact value of Alice's median was, right? So we shouldn't reveal these items to the two parties. And also, in each step, we do a comparison with the secure protocol, say with the circuit, and these bounds should somehow flow away from one comparison to the other, although these are completely different circuits. Okay? It's a circuit for each comparison. So how can this be done? So this can be implemented using reactive computation. I'll show you in a minute, but there's also another way to visualize this. The circuit is essentially composed of layers. Each layer compares two items and also gets the bounds. It outputs an output bit, which tells which of MA and MB is larger. And it also delivers up-to-date bounds to the second layer. The second layer gets these values from this part of the circuit to new inputs, puts an output, and puts additional outputs in. So if you think of a Yao circuit, you can compute this by doing, say, oblivious transfers for these inputs. Okay? Put this output. Only then the party decide what the inputs are to the next step. Then you do oblivious transfers here. So this step gets some wires from this part of the circuit. And here you do oblivious transfers and so on. So essentially what you don't do oblivious transfers for all circuits, for all input wires at the same time. You do it gradually. Okay? But just like one circuit doing comparisons. There is, however, some problem here. If we want to apply the transformation secure against malicious adversaries, like the one Yuda described in the previous lecture, it's not clear how to do it to circuits whose inputs not all come at the same time, but rather come at different phases of the protocol. So it's not clear how to do that. So actually we can have another solution, which is a little bit less clean, but it works. So this is how you implement what we call here. We call this as reactive computation. So it's something like this. In each layer, so ideally this layer should just deliver these bounds to the next layer. Now, suppose we want to put some boundary between the two layers, and we cannot put wires between them. So we can deliver the bounds to the next layer by giving them to the parties and asking them to input them to the computation of the next layer. Okay? But there are two problems here. One is that we don't want the parties to change the bounds, okay? Because then they can cheat. The other is that we don't want to reveal the bounds to the parties, because if A learns B's bounds, she learns what B's median was. So how can we get away from these problems? So what we do, we provide each of the parties with shares of the bounds. So share is just another name for, let's take the bound, say it's 100, and give A and B two numbers which are random except that the sum is 100, or the exclusive O is 100. Okay? So each party gets to share, which reveals nothing. So this takes care of secrecy. We also want to prevent the parties from doing changing the bounds. So what we also do, we give A, in addition to the bounds, MAC, message authentication codes, of the shares that we gave to B. And we give B max of the shares that we gave to Bob. So then what happens in the next level of the circuit, A and B input, in addition to their updated medians, they output their shares of the bounds. the circuit computes the bounds again by adding the two shares. Okay? But another thing that the circuit does is it checks that A provides shares which comply with the max of these shares that were given to B, and vice versa. So this prevents the parties from changing the shares that they got. Okay. So this is how we run the protocol. We still have to prove the protocol as secure against malicious adversaries. So what we want to do, and as usual, show that for every adversary running in the real model, yeah. No, okay, how do we do the MAC, okay? So you can use, I guess, any MAC which doesn't leak information. But, okay, here I'll describe a simple MAC that you can use. So to MAC a value x, okay, I choose two, okay, it's a one-time MAC, but that's enough for our purposes, okay? So to MAC a value x, I choose two random keys A and B, and the MAC will equal let's call it y. So the MAC of x would be A times x plus B. So A and B are the keys, x is the value, and y is its MAC, okay? So this, it's easy to show that this doesn't give information about x because this is pairwise independent because A and B were chosen at random and they're kept secret. So what we should do here is give one party x and also y, and give the other party A and B, okay? And in the circuit, what the circuit should do is it receives x and y from Alice, say. It receives A and B from Bob. It checks if this equation holds. If it doesn't hold, then something bad happens. If it does hold, it continues in the process. So that's not very nice to do it in a circuit, as I wrote here, because multiplication might not be very efficient. But perhaps we can do multiplication in Galois field GF2 to the n might be more efficient, or some other trick. But at least in principle, this can be done. Okay? So it's all that we need here. We don't need a MAC that we can use, like age MAC for many times. Okay, so we want to show here simulation, meaning that for anything that parties do in the real model, you can also do it in the ideal model. So what does the party do in a real model? So basically, they do comparisons, and each comparison it provides an input, and based on the input, it should decide which part of its original input to. Based on the output of the comparison, it should throw away half of its input and continue. That's all they have to do. So we can describe it as a tree. So the first, they compare their medians. Based on this comparison, they have new subset of inputs. They compare these. Based on these, they throw half of their items and so on. So actually, if we know the original sets of the inputs, so based on every comparison, we know exactly which items we need to compare in the next step. So here we have, if we start from sets whose union is n, the size of the union of the two sets is n, we're going to end up with a tree which has n leaves. Okay? And each leaf is going to describe a different value as being chosen as the median. So not really n leaves because, yeah, no. I think it's going to be n leaves. We don't have to care about the boundaries. I'm not sure, but it's either n or n over 2. Probably n over 2. And each execution is essentially a path through this tree. And the execution should make sure that the values reported here are conform to the upper and lower bounds. So what we do know that if a party does not provide a legitimate value to the comparison, that is a median which is between the range, in the range which is allowed to the party, then the protocol aborts. So what can we do now? So what the simulator can do, it has this A or A prime, which is the adversary. It can start doing a simulated execution with A and see what happens. So it does this comparison with A, and it reports, since it's a simulation, it can report to A, it sees what A sends to the comparison, and it can decide, the simulator decides what A receives from the comparison. So say in the first comparison, we tell to A an answer of yes. Okay? So we know this value that A sent, we give him an answer of yes. Then in the second comparison, we also give him an answer of yes. In the third one as well, we get up to here. What we got is that in this path, A gave to us some of its inputs. Okay? Not the other ones, but three of them. Okay? Now we roll back the execution up to this step of the comparison. And before we gave A an answer of yes, now we give A an answer of no. And A doesn't know that we rolled back because it's a simulation. We give him a no, A reports to us this input of his. We go back, we roll back to this step, we tell him no, we get this value, and so on. So by traveling on the tree or simulating the execution with A, we can get all of A's inputs in the simulation. Then we can give these inputs to the trusted party, and the trusted party will give us the actual input of A. Then using this actual input of A, we can finish the simulation. So one other note, I described here the two-party case where there are two parties and they want to compute the median. What happens if there are more than two parties? So we can do a slightly different protocol, which is also good for the two-party case. So if there are n parties, each one of them has an input set. And what we need to know here is the range in which the inputs exist. And suppose we want to find the kth element of the union of the sets. What we can do is do a binary search for that element. Okay? So we set M to be exactly the middle of this range. And we ask all parties to run a secure computation where each party tells them how many items it has which are lower than this M and how many items are larger than this M. Okay? So after each party reports you these values, you sum these values together and you say, okay, if there's a total of 100 items smaller than M and 200 items larger than M, then the median is above M, so therefore I should tell all parties to throw all items they have smaller than M, and vice versa. And if they report that they have exactly 100 items smaller than M and exactly 100 items larger than M, then we found the median. So here too, okay, the number of rounds is logarithmic, but before it was logarithmic in the size of the inputs of the parties, now it's logarithmic in the range. So it might be much larger. Okay, logarithmic in a much larger number. Okay, so even if you only have 100 items, all of us together, but they come from a range of size 2 to the 1,000, we need to have 1,000 rounds. And it's not hard to see that this protocol is also secure. So to wrap up what we did here, we showed pretty efficient protocols for computing the median or the kth value, which is a quite useful statistic. And we had to do this by observing how the function behaves and using generic computation, but just for doing simple comparisons. Okay? And the rest is done by observations about the function. And also the malicious case is not very hard. So one approach doing the malicious case was to use the GMW compiler for all the computation we did. Basically prove that everything that we do is according to the protocol with zero-knowledge proofs. Instead, we only need to do this transformation to secure, to protocol secure against malicious adversaries only for the comparisons, and add these boundary checks as I described before. Okay, so that was the analysis of the median, and now I'll go to the second part, describing another function which is set intersection, which is also quite useful. So the scenario is that we have two parties which have sets of inputs, and they want to compute the intersection of the two inputs. Say that Alice learns the intersection, or the client learns the intersection, the server learns nothing. So I think that you described yesterday two occasions recently that people asked him about whether we can provide secure solutions for secure computation. So both of these cases were for computing the intersection. And I think that most of the times I hear about applications for secure computation, it's about this. Okay? Think about airlines having to provide a list of passengers to the United States government, and the government looking for terrorist names in these lists. So basically they're doing intersections, right? So instead of providing the entire list, you can compute these intersections. And intersection is really one of the most basic things you want to do. So you can think about many things like credit rating, looking for terrorists, dating, looking at mutual interests, or instead of just learning the mutual interests, instead of learning the intersection, you can say compute a bit which is 1 if the number of shared interests is larger than something and 0 otherwise. So if two people have lots of shared interests, you'll match them, otherwise you won't. So you can think of many applications here, genetic testing between two parties and so on. So suppose parties have genes for parties. A man and a woman have genes for specific diseases, and you don't want two that have genes. There's a pair that together there's a risk of them bringing children with some disease. Okay, so you don't want to reveal to each other, the genes that you carry, but you want to compute maybe in advance that not both of you are carrying the same gene. Okay? So you can do things like that with this functionality. So at first, let's look at trying to implement this using a circuit. So the trivial circuit will take all pairs of values and compare them, but then the circuit will be of size n squared. And if n is 1,000,000, that's quite a lot. A more advanced circuit could do something which is a bit smarter. So we could take the union of the two sets, sort them together. And then if Alice and Bob have the same item, the two items will be right next to each other after we sort the items. Okay? So after we sort the items, the circuit have to look at every two pair of adjacent elements, see if they're both equal, meaning that they came from Alice and Bob, therefore they're in intersection. So what's the size here? The best circuit for doing sorting is the AKS sorting network of size n log n. So we can have a circuit of size n log n for computing the sorting, and then the scanning is linear. So we can do this in circuit of size n log n, apply Yau's protocol here. So the problem with this construction is that the constant here is quite large, something like 6,500. There's another construction of a sorting network of Butcher, which has 2 log n square gates with a small constant. So we can have a circuit of size 2 log n squared, but I'll show you a more efficient protocol. So the basic tool we're going to use is additively homomorphic encryption. Yeah. Yeah, so as you said, if I do this sorting, I must make sure that, if say, malicious Bob, if I just look if there are two elements which are equal right next to each other, then and I don't check if one of them came from Alice and the other from Bob, then Bob could provide two inputs of size 10, say. In the sorting, they'll be right next to each other, and I assume that one of them came from Alice and one from Bob, and I'll declare that there's intersection there. So we have to handle these issues. I guess this is a malicious Bob, the one you described. We have to handle this for the malicious case. Actually, I'm not going to describe the malicious case. I'm just going to describe techniques for the semi-honest setting, but we have nice enough techniques for the semi-honest setting. It's interesting enough by itself. So a tool that we're going to use is homomorphic encryption, so only additively homomorphic encryption. So I assume most of you heard of it, but let me just repeat. So it's a public key encryption, E, so that just giving the ciphertext alone, E of X, it's possible to do additive operations on the plain text. Namely, giving E of X and E of Y, we can encrypt the encryption E of X plus Y. And I just why because this is how we implement it more or less. E of X plus Y is the multiplication of E of X and E of Y. I just write it this way. I'm abusing notation here. And another thing we can do is, given an encryption of X and some constant C that we know, then even without knowing the decryption key, we can compute an encryption of E of C times X. So actually this property comes from the first one. So to encrypt the encryption to compute E of 2X, I have to add an encryption of X to itself. And similarly, you can compute any encryption of C times X with the number of additions, which is logarithmic in C. So you can do it efficiently. And actually the way you do it, which is essentially the same way at the end, is you take E of X and raise it to the power of C. This is how we're going to write it. And this is useful for many applications. For instance, it's useful for voting. So a naive voting protocol could ask parties, each party to say encrypt either 1 or 0. And then if we want to decide, to find out how many people voted in favor, we sum all the encryptions, we decrypt, and we learn how many people voted in favor. Of course, there are many issues here. If I want to cheat, I can encrypt, say, 100 instead of 1, and I'll count as 100 votes. So you have to do other things. But this idea is behind many protocols for voting, which of course adds some other layers of security over this. And you can also do oblivious transfer using homomorphic encryption. Yuval Ishai, Aiello, Ishai, and Weingold have a nice protocol for oblivious transfer based on homomorphic encryption. You can do many things just with additively homomorphic encryption. So standard public key operation functions do support multiplicative homomorphic properties. So in RSA, if we encrypt 2 ciphertexts, we get the encryption of the multiplication of the plain text. The same is true for El Gamal. So in El Gamal, this is the ciphertext. So if we encrypt 2 ciphertexts of M1 and M2, we get an encryption of M1 times M2. So these are homomorphic with relation to multiplication. So suppose we want to do addition. So one thing we can do is use modified El Gamal, where instead of encrypting M here, we put G to the power of M here. Here I assume that people know what El Gamal encryption is. So now when I multiply 2 encryptions, I get here G to the M1 plus M2, e to the G to the power of the sum of the 2 plain texts, which is the encryption of M1 plus M2. Now I do have a problem here. When I try to decrypt, I get G to the power of M1 plus M2, and now I have the problem of finding what M1 plus M2 is, right? In El Gamal, we needed the H assumption, which implies that discrete log is hard. So how can I find M1 plus M2 here? So it is hard to find this value so it is hard to find a discrete log if the exponent is random, but if it's not random or if it's small, then it's easy to find. So suppose if I know that M1 plus M2 is small, say it's the number of people who voted, say, in this country in favor of a certain party, so it's less than 5 million or 7 million, so I know that here I have G to the power of something which is smaller than 7 million. So I can just search over all numbers or use some other efficient algorithm for computing discrete log, like baby step, giant step, which can work pretty good, I would say, until numbers which are, say, 2 to the 60 or so. So if we only care about numbers of that range, we can do pretty easy homomorphic encryption. Another homomorphic encryption function is Paillet's crypto system, which is based on the composite residuosity assumption. And I won't describe the properties, but it's widely used, or at least widely used in cryptographic papers. And it works in the group Zn stars, Z n to the power of 2 star. So namely in the residuostic class modulo n square, where n is a RSA modulus. So I won't go into details, but it's a widely known and used encryption scheme, which is additively homomorphic. Okay, so now we go back to the intersection problem. I described the protocol to you. So what the client does, it defines a polynomial of degree n. N is the number of items the client has, whose roots are the inputs of the clients. So if the client has inputs x1 up to xn, it defines this polynomial, and you see the roots are exactly the inputs of the clients and nothing else. So this is one way to describe the polynomial. Another way is just to describe it using coefficients, a0 up to ak, okay, if it has k items. So k here should be n. Okay, if it has n items, polynomial should be of degree n, and we should have n here. Okay, so this is n. Now the client sends to the server homomorphic encryptions of each of the coefficients. Okay? Now what does the server do? Note that if you get homomorphic encryptions of the coefficients of a polynomial, you can evaluate the polynomial. Because look at p of y, or encryption of p of y, where p is the polynomial, is the encryption of a0 plus a1 times y plus a2 times y squared plus plus plus. Okay? Now, y is a value which is known to the server, and it gets encryptions of the coefficients. So what it can do, it could take the encryption of a0 which it receives, and take the encryption of a1 and compute the encryption of y times a1. So before I told you, given encryption of x, you can compute encryption of c times x. So here we get an encryption of y, of a1, and compute an encryption of y times a1. You get an encryption of a2, and compute an encryption of a2 times y squared, and so on. And then you add these encryptions, and you get an encryption of the value of the polynomial. Okay? So the server, even though it cannot decrypt, computes the encryption of the value of the polynomial applied to each of its items. Now note that this value here, if an item is in the intersection, it's 0. If it's not in the intersection, then it's not 0. So we could have thought about sending in these values immediately back to the sender, to the client, okay, which can decrypt them. But that's not good. That won't do, because indeed, if we send these values to the client, for each item in the section, the client receives a 0. Now, suppose it receives an encryption of 5. So it knows this doesn't correspond to any item it has in the intersection. But since this polynomial was defined by the client can think, okay, what is the y such that p of y is 5? Okay? And since the client knows what p is, it might find that y. Okay? So therefore it knows that the server has this input y, which resulted in this 5 as 5 being p of y. Okay? So we cannot just send these items. So we do something else. So for every y, or for every yj of the server chooses a random value rj, and it computes the encryption of p of yj multiplied by this random rj plus yj. So what do we get here? We get that if yj is in the intersection, this is 0. rj times p is 0, so therefore we get an encryption of yj. If yj is not in the intersection, then rj times p of yj is random. And since it's random, it completely masks the yj we add here. So what we get here is an encryption of something which equals yj if yj is in intersection, and it's random otherwise. Okay? So S sends its value back to the client. It must send them in permuted order, so the client doesn't learn anything from the order of the items. The client decrypts. Suppose that the range is very large, okay? Much larger than the number of items that the client has. So if she sees a random value if she sees in decryption a value which is not in her set, she knows that no match was found. Say that she finds decrypts and sees the value 5, which was already in her set. Then either 5 was generated because here we computed r times 0 plus 5, meaning that 5 is intersection, or 5 was generated because somehow r times something which is not 0 plus something happened to be 5. But if the range is large, this happens with very small probability. So therefore, if she finds one of her items in the values she decrypts, she decides that this item is in the section. Okay. So that's the main protocol. We can change it a little bit. Suppose we just want to compute the size of the intersection rather than the number of items in than the exact items. Then actually you can compute, instead of adding y here, you can add 1. So Alice would check the number of ones she receives. Actually, you don't have to add 1 here. You just send rj times p of yj. So for a value which is in intersection, Alice will receive a 0. If it's not intersection, she receives some random value. And there's another variant which enables to compute whether the size of the intersection is larger than some threshold. Say Alice and Bob match if they have more than 10 common interests. So why is this secure? So think about the security of the client, at least in the semi-honest model. So the server just sees encryptions of coefficients. If the encryption scheme is semantically secure, then the server learns nothing from these encryptions. Okay? So therefore it learns nothing. Seeing encryptions of certain numbers is just like seeing encryptions of other numbers. So we can simulate the server's view by just sending it encryptions of arbitrary numbers. What about the server's privacy? So can this client simulate her view? So what the client sees, she gets a permuted list of encryptions, which includes encryptions of the values in the intersection and encryptions of random values otherwise. So given the client's input, or at least the number of her inputs, and the size and the values in the intersection, we can simulate the client's view. We should send back to the client a list of encryptions, which includes encryption of the items in the intersection, and as many random numbers as we need. So that's her view, and therefore she learns nothing from the protocol. That's great. So what about efficiency? So the communication is linear. The client sends n items and receives back n items. What about computation? The client encrypts n coefficients, and she decrypts n encryptions. That's also great, because we cannot hope to do anything better than linear here, because we have to touch every item in the inputs. But what about the server? The server has to evaluate a polynomial for every item in his input. So for every y it has to evaluate this polynomial. The polynomial is of degree n. So therefore the server has to do a total of n squared exponentiations, which might be large. Think about n being, say, 1,000,000. Okay? So 1,000,000 exponentiations is something you can do, but 1,000,000 squared is already, it's too much. So we'd like to reduce this number. And n being 1,000,000 is exactly what the numbers, the range of numbers which are interesting to the parties involved who are thinking about these applications. So one way of thinking about, so here I'm going to describe a set of optimizations which reduce the overhead. The one is just a simple observation. Usually the numbers, the values come from a small range, say like 20 bits, or more than 20 bits. We represent names, okay? So if we have names, say there are up to 1,000,000 names in the world, okay? We can hash them to a range of size 20 or 40 bits or something like that, okay? So everything is rather small. Now, instead of computing polynomials as we usually do, we can compute polynomials using good old Horner's rule, which I learned, I think, in the first class I learned in computer science. It was Horner's rule about evaluating polynomials. So, okay, for those who don't know it, that's another way of representing polynomial. And what's nice here compared to here is that you always multiply by y. You don't multiply by y squared, y to the power of 3, and so on. You only multiply by y. So why is this important? If we start from a y which is, say, 20 bits long, if we look here at exponents of y, y become larger and larger. They become larger and larger. And say we work in a field of length 1,000, so and n is, say, 1,000,000, quite quickly y to the power of j, where j goes from 1 to 1,000,000, will be a value which is 1,000 bits long. So here we have to multiply by long values, and this multiplication, because we do it to the homomorphic encryption, translate to exponentiations with full-size exponents. If we use this Horner's rule formula, we always multiply by y, which is a short, say, 20-bit number. Okay? So if this translates to exponentiations, we use an exponent which is only 20 bits long. So if we think about exponentiation as something whose overhead is linear in the length of the modulus, which is not true because there are different optimizations like Tsuba and other optimizations, but say it's true, then we get here an optimization by a factor which is the size of the modulus we use over the log of the range of possible items we have. And say if this is 1,000, this is 20, we get an optimization of about 50. Okay? Which is constant, but this constant seems to matter. Okay? So now we get from n square log exponentiations to n square short exponentiations, but we can do better. Another technique we use here is something I like to use is hashing, combining hashing here. So suppose we want to hash items to bins or throw balls into bins. So we have, say, k or n items, and we have a hash function, and we want to throw these items into b bins using a random hash function. So the hash function should be independent of the inputs, and we just throw them into bins. And let m be a bound on the maximum number of items that fall into a bin. So if we think about this process of throwing items to bins or ball to bins, there are well-known bounds saying, if I throw n items to n bins, I expect to see up to, in that case, log n items in a bin with probability of at least this and that. Okay? And there are there's well-known analysis, at least for the case of throwing n items to n bins. Okay? So if I know that with overwhelming probability I won't have more than n items falling into a bin, I can use it in my protocol. So this will work like this. The client will choose a random hash function and will throw the items it has its input into bins. Okay? And then it knows a priori that with very large probability not more than m, say 20 items will fall into each bin. So therefore he'll handle each bin separately. So for each bin it will define a polynomial as before of degree m. Okay, where m is the bound on number of items falling into a bin, say m equals 20. Now each polynomial encodes the items mapped to that bin. And if for a certain bin we had less than 20 items falling there, we'll use a polynomial of that degree, but would add dummy items like 0. And we know that 0, say, is an input which none of the parties should have. Then in the protocol, the client sends to the polynomial the hash function, and also the polynomials P1 up to PB, one for each bin. The polynomials are those of small degree, of m degree. Now what should the server do? So the server, suppose it has the number 7 as one of its inputs. It knows that if the client had the number 7, it would have thrown that number into the bin age of 7, right? So therefore, it should evaluate 7 only against the bin, the polynomial of the bin age of 7. age applied to 7. So now what the server does, for each input y that it has, it checks what is the bin to which this item would have been mapped by Alice, and then evaluates the polynomial exactly as before, but only the polynomial of that bin, and sends the result back to Alice. So what do we gain here? We gain that these polynomials are likely to be of much larger degree than n. So now the server will have to evaluate polynomials of a much larger degree. So let's see what happens. Yeah.
You choose the hash function, so you try to make sure that there aren't any collisions. Otherwise, you choose a different hash function.
No. So there are collisions. We throw items into bins. We don't require that only a single item will be mapped to every
So
bin.
there won't be more than m, is what I mean.
Okay, so
Probably there won't be more than m in any bin.
so that's actually a
Not
very
negligible.
okay. It's a very luckily. Okay, so that's actually a great question. So as I said here, we should hope that not more than n items will be mapped to a bin. Okay, if more than n items are mapped to a bin, then we're in trouble because we don't have room for them. We would like the probability of this bad event happening to be very small, actually negligible. Why is that? Because if we map more than m items, because okay, what can we do if Alice does a computation and sees that she maps more than items to a certain bin? What Alice can do is choose a new hash function, repeat everything, and then send a new hash function to Bob. But in that case, Bob can do this thinking. Okay, I receive this hash function from Alice. It's not a random hash function. It's one which Alice chose so that it fits with her inputs. So therefore, I can start thinking about possible values for Alice's input, which are not good for this hash function because they'll deliver more than n items to a certain bin. And therefore, I know that she doesn't have these values. So it's important that Alice will choose a random hash function, and that with huge probability it will be a good function. So actually, for this and another option is that if this event happens, Alice will just say, okay, I get a collision, more than n items, let me just forget about one of my inputs, and I'll compute another function. Okay, that's not good as well. So what we should have is to have a result from those who examine this function saying that the probability of more than m items falling into a bin is negligible. Okay. So unfortunately, they usually don't care to do this analysis. Fortunately, for the functions that we do care about, there is similar analysis. Basically, or specifically, in a few slides, I'm going to talk about power of 2 hashing, where you choose one of two bins. I'll describe it in a few minutes. And for that function, there is an analysis by Broder and Mitzenmacher showing that the probability of this function, this bad event happening, is negligible. Something else that you can do, even if there's no analysis, as a say practitioner, you can start running simulations. And suppose if you do 10 billion simulations and nothing happened, you can say, okay, I don't know better than this, but it's at least the probability of a bad event happening is more than 2 to the minus 30 something. But here actually we depend on probability analysis of these bad events not happening. And what's annoying here is that people who do investigate these hash functions, usually they're happy if the hash function is good with good probability. So they don't want the bad probability to be negligible. It's enough for them for that bad probability to be 1 over n, or even 1 over square root of n, or something like this. So we have to do the analysis to find out that the bad probability is lower than that. Okay, so what's the overhead? So the communication is the number of bins times the degree of a bin, the bound of the number of items that fall into a bin. That's b times m. And the work of the server is for each of its items, it has to evaluate a polynomial of degree m, okay, which is the bound of number of items that fall into a bin. So how large m should be? So if you just throw items into bin, it's known that if you throw n items to n bins, then m is something like log m. Okay. So therefore, the communication is increased to order of n times log n instead of order of n, but the computation of the server is reduced to n times log n. So we can actually do better than that. So there's a very nice hashing scheme called balanced allocations of Azar, Border, Bar-Ilan, and Upfal, which goes like this. Instead of just throwing items into bins, I use two hash functions, h1 and h2, and an item could be found, an item x, you throw it either to h1 of x or to bin h2 of x, to one of these two bins. How do you decide? When you want to put the item in the bins, check which of the two bins, h1 of x or h2 of x, is more occupied, and put the item in the bin which is less occupied. So each item has two options. Put it in the bin which is less occupied. Okay? And these guys showed that if we set the number of bins to be n over log n, then with high probability, and here there's an analysis for this probability, okay? The maximum size of a bin is order of log n. So what's nice here is that we reduce the size of the bin from log n to log n, this bound log. So if we plug this into the formulas we had in the previous slide for the overhead, we get that the communication is b times m, which is linear, and the server's work is n times log n, where log n, no, so if n is less than 2 to the 30, log n is less than 5. Okay? So it's 5n for any practical purpose. What's a little bad here is that the client now doesn't have to check a result only in one bin, but in two bins, because every item might be in two bins. Also, the server doesn't have to evaluate a single polynomial for every item, but two polynomials. So instead of a single polynomial of degree log n, it has to evaluate two polynomials of degree log n. But this symptotically, this looks very nice. Now we can do even better. So we can use cuckoo hashing, which I won't describe the details, but it maps n items to something like 2n bins, slightly more than 2n bins. And the bins now have constant size. So an item can be found either in bin h1 of x or in bin h2 of x, or in another place which we call the stash, which can be of small size, say size 3. Okay? So for stash of size 3, the probability of the functions not working is n to the power of minus 3. So if you're willing to have this probability of a bad event being n to the minus of 10, we need a stash of size 10. So now each item might be each item y is either in bin h1 of I, h2 of y, or in the stash. So in each bin we're going to have a single item. Okay? So each polynomial is going to be of size 1. And the stash is going to have a polynomial say of degree 3. So now the server has to compute two items, two polynomials, but they are linear polynomials. So now the server, for each of its inputs, has to evaluate polynomials of two bins, which are linear, and the polynomial of the stash, which is of size 3. So 3 polynomials, all of constant size. So the overall work of the server is now linear. And the same is true for the communication and for the client work. So here we get very nicely to linear overhead. So this seems like the ideal solution that we have. So that's the best we can do. And then we set up to actually examine these results. Okay, and we did some experiments. So here are the experiments. So the asymptotic runtime for the 3 versions we had: the random mapping, the balance allocations where we mapped item to one of 2 bins, we mapped it to the least occupied bin, or the cuckoo hashing. So the asymptotic runtimes are n log n, n log n, and n. Now, for say here for n equals 10,000, what are the actual runtimes? So there are 48 seconds, 69 seconds, and 65. Okay. Something here is wrong, okay? Because according to this, the overhead should go down, and here it goes up. Okay? And here we have a graph. So this red line is what happens if you do no hashing. That's the n squared. And n squared, pretty early, you cannot use it anymore. And these three lines are next to each other, I mean, compared to the n squared. But if you look at them, the top one, which is the least efficient, it's probably its combination of balanced hashing and cuckoo hashing. And the more efficient is the basic hashing, the n log n result. So why is this? Why is the n log n overhead better than the other overheads? So I must tell you, it took us months to find the answer. Not months of constant work, but months of looking it back and doing other things, and then examining it again and looking at the code, and measuring again and looking for bugs. And so here's the answer. So what the server actually computes, it doesn't only compute a polynomial. It computes the polynomial, and then it multiplies it by r. R is an exponentiation. Now we call that computing the polynomial is exponentiations with short exponents, and this multiplication by r is with a large exponent. Now here we do, if the polynomial is of degree d, we do d short exponents, but regardless of what the degree d is, we do this multiplication by r, which is a large exponent. So if we put it together, the overhead of this multiplication, it's something like 6.5 short exponentiations. So what we get is that if we evaluate a certain polynomial, the overhead is linear in the degree plus 6.5. So 6.5 is just for this multiplication by r. So now what happens? If with different methods, the server evaluates one polynomial in the simple hashing, two polynomials of slightly lower degree, log n instead of log n, in the balanced allocations, and three polynomials in the cuckoo hashing. Now, in the last two methods, we use polynomials of smaller degrees. This means that the d is smaller. But for each polynomial, before we start thinking about the d, we pay this 6.5 overhead just for multiplying by r. And it kills everything. So think about log n compared to log n. Log n might be 20, log n might be 5, okay? But then we add 6.5. When you do the lower one, you do twice. So you compare 26 to, what did I say? 12, I guess, or 13 times 2, which is also 26. And also, okay, it's not really 20 and log of 20 because it's only asymptotic here. So if log of n is 20, but log n, when you do the actual overhead and look at the constants of actually what's the size of the bin that you need to get is slightly larger than s, then you pay here more. Okay? And the same is true with the cuckoo hashing, where you have to evaluate three polynomials. So simple hashing is better. This doesn't say that the more advanced techniques won't be better asymptotically, but you'll have to go to huge inputs in order for them to pay off. And I don't think that anyone's going to use these methods for inputs of that size. Okay. So this is actually a very good lesson. It's a lesson good in both directions. First, it shows that you get a basic scheme, and then by using material or ideas from a different area like hashing, you can make it much more efficient, or at least asymptotically. And then the second lesson we got is that something which is efficient asymptotically might not be efficient in practice. And if you actually want to implement this, you have to think about the actual overhead of the implementation. And this is by no means trivial. As I told you, we spent months trying to figure this out. So, question?
Yeah, you said this was for 10,000?
Yeah.
And your clients had asked for like 1 million stars they were comparing the astronomers?
Yeah. So, okay. So for 10,000, it was something like 40 seconds. Okay. But this is just, implementation we had. So assume that, a good implementer will do it in 20 seconds. So for a million, it's 100 times 20, it's 2,000 seconds. It's an hour.
Yeah, not larger end, so maybe the asymptotic more.
It might be, you'll have to check. But okay, to do this okay. So these graphs, okay. Okay, we didn't print these graphs from a single run of the protocol. We repeated each run like 100 times. Okay. And we did it for many, okay, also the question is what is log n and log n? We did different experiments. So we couldn't continue checking, so we have some experiments. So the last number here is 10 to the power of 6. Okay, it's 10 to the power, you cannot, it's 10 to the power of 6. But we couldn't do testing for larger n because then it would take more time. But definitely up to 10 to the power of 5, we can do experiments and repeat them over and over again to get results in which we believe. More questions? Okay, thank you.